the Bacon shortcode because Bacon discovered it. And it's based on the short
Yeah,
code.
okay.
But really, I guess it's Bacon's code. Right, but so the idea is we're going to start with this short code. So the short code was a 9-qubit code, and here I've written it with the inner code is the repetition code. So ZZI, IZZ, the standard repetition code, classical code. The outer code is the dual repetition code. So this is logical X for this code, logical X for this code, logical I, logical I, logical X, logical X. Logical X commutes with ZZI and IZZ. That's what we want. And so this is a CSS code. This is the code we've seen before. 1, 2, 3, 4, 5, 6, 7, 8. 9 minus 8 is 1. Good. And yeah, as I said, this code is, or as we've seen, this code is, the X operators are different from the Z operators. So it's a CSS code, but it's not self-dual.
Yeah.
But it's sort of self-dual. I mean, no, I don't know, it's not at all, but there is some similarity. So for example, if you multiply the first, this guy, and this guy, you get this weight 6 stabilizer. If you multiply the second one of each one, is you get this weight 6 stabilizer. And that, if I arrange them on a grid, it looks like this. So here it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this X stabilizer is 1, 2, 3, 4, 5, 6. It's these two rows. This X stabilizer is 4, 5, 6, 7, 8, 9. It's these two rows.
Yeah.
And these two stabilizers is 1, 2, 4, 5, 7, 8. 1, 2, 4, 5, 7, 8. So it's two columns.
So you guys put the rotated there.
And this guy is 1, 2, 3, 4, 5, 6, 8, 9. 2, 3, 5, 6, 8, 9. So it's these two columns. And so those stabilizers they're almost the same as each other, just like flipped by 45 degrees or transposed or whatever. All right, so that part is sort of self-dual up to this flipping operation, but of course it's still not self-dual because you still have 4 more Z stabilizers than the next stabilizers. All right, but this is still interesting because like we know that these two stabilizers are enough for Z errors to correct the Z errors,
Yeah.
because the code corrects, it says distance 3 in the Z direction. So these guys have to be enough to correct X errors, because these guys are the same as these, up to the transpose, up to flipping by 45, up to reflecting, whatever. And so what's the point of these stabilizers if we don't need them to correct X errors? So that was Bacon's observation. We can just throw away these stabilizers. That'll give us so I only keep these 4 stabilizers.
Yeah.
And it's almost self-dual. So that'll give us a 9-qubit code that has 1, 2, 3, 4 stabilizers. So that's 9, 5. So if I only use these, I'll get a 9, 5, 2 code. I mean, it's not distance 3 anymore because like
Right.
this is a weight 2 logical operator.
Yeah.
It commutes with all these stabilizers, and it's not itself one of them. So we only get distance 2. But the interesting thing here is these 5 qubits, some of them have distance 2, like these 4 operators. But it turns out, actually, oh, there you go. So these 4, this is like logical Z on qubit 1, logical Z on qubit 2, logical Z on qubit 3, logical Z on qubit 4. But on that 5th qubit, logical Z will have weight at least 3. So there's unequal protection. One of the encoded qubits will have distance 3, and the other qubits will have distance 2. And that's what this subsystem stands for. So subsystem means that there's different protections for different encoded qubits. So here I've written it all out for us. Good. So these are the 4 stabilizer generators. Here's logical qubit 1. It's just transversal X. So these anticommute with each other because 9 is odd. Yeah. This commutes with all these. This commutes with all these. So that's a valid logical qubit. And these are the other 4 logical qubits. And you can check like these anticommute, these anticommute, these anticommute, these anticommute, everything else commutes. But so these guys only have distance 2. You can see they have weight 2. This guy has distance 3. What I mean by that is that, I mean, it looks like it's distance 9, but actually, like if you multiply this times this, you get XXX, so that's distance 3. But furthermore, even if you multiply these logical operators by any combination of these guys or these guys, you still have always a weight at least 3. There's no way of affecting this first logical qubit without at least a weight 3 operator, even though you can mess up the other encoded qubits. And so that's the idea, is if you have a weight 1 error, like a y error in qubit 5 in the middle or something, and you try to correct it using by measuring these syndromes, you can't correct it because the code only is distance 2. But so there's not a unique correction, but you can apply some correction to it, which will leave the first logical qubit alone, and it might mess up these other 4 logical qubits. And the important part is we're leaving the first logical qubit alone, so that's where we put our information. We don't care about that stuff. So that's called a subsystem code, and these are rather nice. So you were talking about what codes are practical. This code is looking more practical. Why? Do I have it here? Okay, I have a few reasons in the notes. Let me just try to draw it. It's easier to see it in the picture. So again, these are my 9 qubits. The X operators are pairs of rows. The Z operators are pairs of columns. And actually, just trivia, of course this generalizes, right? So there does exist a 25, 1, 5 subsystem big and short code, right? So pairs of rows are X stabilizers, pairs of columns are Z stabilizers. Okay, that doesn't really matter though. Right, so what I wanted to say is, okay, this is hard to draw. Let's see if we can do it. So these are my X stabilizers. So now a logical Z operator should commute with the X stabilizers. What does that mean? A logical Z operator, well, for example, 2 Z's in the same row will definitely commute. It's like 2 Z's here, 2 Z's there, 2 Z's here, 2 Z's here, whatever. Any 2 Z's in the same row, that's a logical operator. So that's what these guys are. This is like 1, 2, 3. That's 2 Z's in the same row. That's 2 Z's in the same row. That's 2 Z's in the same row. Yeah. So that's what's going on there. Right, and then similarly, 2 X's in the same column is going to be one of these guys, like 1, 4. That's 1, 2, 3, 4, which are in the same column. So 2 X's in the same column is a logical operator, but only on these extra qubits. These qubits are called gauge qubits, because we don't care what they are. Okay, and so here's the cool thing. So instead of measuring this weight 6 operator to do X error, to measure the X stabilizer, instead what I can do is I can just measure X1, X4, and measure this, where was it? Yeah, this logical X operator. And I can measure X2, X5, which, okay, it's not one of these, but it is a logical operator for a gauge qubit, or a combination of gauge qubits. So I measure 1, 4, 2, 5, 3, 6. Those are all logical operators. And then once I measure those operators, the product of those measurement outcomes gives you 1, 2, 3, 4, 5, 6. Or the sum mod 2. The product if they're plus or minus 1, or the sum if they're 0, 1. And the same here. So I measure 4, 7, 5, 8, 6, 9 independently. So those are 3 logical operators, but therefore they mess up the gauge qubits, but I don't care. They're the gauge qubits, so I'm not storing information in those qubits. So even though you're measuring them, who cares? But the product of this operator, this operator, this operator together gives you this weight 6 X operator. And so that gives you all the information you need to get those 2 syndromes. So that's the idea, is we measure the x operators vertically, just two at a time, and the z operators horizontally, two at a time. That gives you all the information you need to get these four stabilizers, which lets you then correct errors on the first, on the important encoded qubit. And so even though the stabilizers have weight 6, you only need to do 2 qubit measurements. And they're nicely geometrically local if you arrange the qubits in a square, like in a lattice like this. Yeah, so physically that's a pretty nice property.
Especially for superconducting, right?
Yeah. Weight 2 measurements, and you get a really nice code. And this code, I mean, maybe it's not as good as 2317, but it's quite a good code actually. Like, it has very high threshold. This 913 code, making sure code. Okay, so this kind of messes up your head though, because you have all these gauge qubits, and that's why it's more confusing.
Yeah.
With different protection. Yeah, and I don't know of any table of subsystem codes. I'm not sure what you look for, right? I mean, I'm not sure it even makes sense to have a table of optimal subsystem codes, because what does optimal mean? I mean, this code, like 913, is definitely far from optimal. The reason it's interesting is because its stabilizers have this nice pattern, and you can't really optimize that. I don't know. It's not clear. Okay. So I guess one other thing that's interesting, if you look at like the code we started with, where there's an asymmetry between the x and the z stabilizers before we converted to the Bacon short code, by throwing away these guys. Let's see. Yeah, so logical x for this code was just x to the 9, x tensor 9. Logical z was just z tensor 9. Well, let me see. If you look at this code here, logical 0 is a state that's stabilized by all these plus. Oh, here, I don't want to do that. Let's look at logical plus. So logical plus is a code that's stabilized by all these 8 stabilizers plus logical x and logical x. So logical x is x transversal, x on all 9. But if you have x on all 9, multiplying by this guy gives you just x on the last 3, or x on the first 3, or x on the middle 3, multiplying by both of these. And so in other words, logical plus, it breaks into 3 copies of the stabilizer XXX, CZI, ICZ. And so logical plus is just, it's equal to a cat state tensor 3, like that. Did you see what I did? Because once you have x to the 9, you can just, multiplying it by this guy, you can break it into just three independent 3 qubit states. There's no entanglement between them. Okay, so that's logical plus. Logical 0 is not so easy, because logical 0, you have to add the z stabilizer, and it doesn't break into 3 parts or anything. So there's just asymmetry. But in the Bacon short code, everything's symmetrical again. So you can actually say that logical plus. Well, what do I say? Oh, here. Okay. Yeah. So I guess plus on the first qubit and then logical 0 on the other 4 gauge qubits is going to just be what I just said. Three copies of a cat state, but it's also symmetrical. So logical 0 and then logical plus on the 4 gauge qubits. That's going to equal the dual, because everything's symmetrical. Plus minus 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 tensor 3, except it's not really. It's this state but rotated by 45 degrees with the transpose. So that's why I wrote it like this. 147, then 258, then 369. Okay, so that's a nice property of the Bacon short code. Other nice properties, you can apply Hadamard. So the way you apply an encoded Hadamard is you just apply Hadamard on every single qubit, then you move them around. Because you to do the transpose, you to switch them around to make the x's horizontal and the z's vertical again. This is the most important property, the fact that you can measure the stabilizers just with weight 2 operators. I'll talk about this later. All right, so I'm basically out of time. I think we've covered a lot of material. Maybe one last piece of trivia in the last couple of minutes is why do we worry about codes quantumly? It's not a problem classically. And I don't know. I mean, I'm not a physicist, but this is a story people tell. So I can tell you sort of a standard story. Maybe you guys can figure out if you believe it. So the idea is has to do with sort of magnetism. So magnets are like atoms, and they like to point in the same direction. I think that's a magnet.
That's a ferromagnet.
It's a ferromagnet, exactly. Yeah, and so for example, you can use ferromagnets to store memory. I think that's what a lot of computers do. Like the way you store a 0 is by pointing them in one direction. The way you store 1 is by pointing them in another direction. And in one dimension, this is a bad idea. So if your atoms were lined up in a line, this would not be stable, because if you have an error, if one of these flips from up to down, from 1 to 0, now I have the energy penalty. I have a weight 2 energy penalty. You have a penalty for every time two adjacent atoms are different direction, pointing in different directions. And that could spread out, because even if you have 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, that whole thing only has the same energy penalty. So the length of the error could increase without penalizing it in terms of energy. That's bad. But in 2 dimensions, and actually something more physical, like in a 2-dimensional magnet or something, or even a 3-dimensional magnet, that kind of thing doesn't happen, because if you're storing your information in a 2-dimensional lattice of atoms, and the all 0, and you want to have you want to have encoded 0, which is everything pointing down, say. In an island, an error starts to appear where some of them are pointed up. The energy penalty is like the perimeter of the island. That's the number of terms that cross from 0 to 1. And for this island to grow, to take over everything, to flip logical 0 to logical 1, this island would have to grow, which means the boundary would have to grow, which means the energy penalty would have to grow. And so that's not very physical. It's hard to get higher energy into your system. Okay. Yeah, so that's what I'm trying to say here. To go from logical 0 to logical 1, you need to cross over this high energy barrier. But not in 1 dimension. Okay. Right, so the question is, can you come up with some quantum analog to a ferromagnet that stores 1 qubit with a local Hamiltonian, like 2 qubit terms, but I guess not in 1 dimension, because you can't do it classically, but say in 2 dimensions, such that still to change from logical 0 to logical 1, to apply the Pauli operators or whatever that change you 1 qubit at a time from logical 0 to logical 1, the energy penalty, well, you like it to grow just like in the first picture, linear in the size of the system. And that's, so this is what's known. So these kinds of codes are called self-correcting quantum codes. They do exist in 4 dimensions. If you have a 4-dimensional lattice of qubits, if you can imagine that. There's evidence that they don't exist in 2 dimensions. I don't know if it's 100% proved. There could be loopholes in the proofs. They're pretty strong proofs, but I don't know, there could be a loophole. Like one loophole could be that maybe a subsystem code could work, because a lot of these proofs don't hold for subsystem codes. In 3 dimensions, I think it is possible. Probably. I don't know why I say probably. I think it is possible. Yeah, it's just more recent. then people have been able to do that. So I guess that's one reason why it's harder to build a resilient quantum memory than a resilient classical memory, just because you need more dimensions, it seems. Plus, even if the code exists, you still need to like engineer the system to have that interaction, which isn't trivial. But anyway, that's kind of fun. All right, cool. So I've introduced codes today. Next time I'll talk about how we actually use the codes. That's called fault tolerance.